We're at lecture 8, almost halfway through the course now. It's getting a bit busy, so I've had to recruit some help to prepare some of the slides here. Hopefully it all works out well. So lecture 8 is on Lagrangian mechanics, and you'll remember back in lecture 3 we did like a really simple intro to Lagrangian mechanics. We changed subject for a little while to let it set in your head, and then we came back to this block, lectures 7, 8, 9, and a bit of 10, to look at Lagrangian mechanics in a lot more detail. And so last lecture, lecture 7, what we did was look at calculus of variations to put sort of a calculus-based footing behind the idea of variations in paths and looking for the path being minimized or stationary. Today, in lecture 8, what I want to do is focus a little bit more on Lagrangian mechanics, and it will be a little bit more of a lecture perspective looking at technical detail of the subject. And then next lecture, lecture 9, is going to be pretty much all examples of how to use it to solve real problems. Okay. So one of the questions that comes up usually at this time of the course is why we like Lagrangian mechanics so much. And there's basically two reasons to this. The first is that Lagrange's equations take a very similar form in pretty much any coordinate system. You use the same approach no matter whether you're using polar coordinates or Cartesian coordinates. And that's not something that you find with Newton's equations approaches. And it's nice because it means that the solutions to the problems are a lot easier because things look quite similar. The other aspect of this is comes in treating constrained systems, and we haven't discussed constraints yet. It's later in the lecture. But to give you an example, it's where the motion is restricted in some way. For example, in a pendulum, you've got a mass connected to a spring, and it can't really go all over the place. It's subject to the constraint of the string making its motion follow a certain path. Okay, and you'll know from first year when you deal with those sorts of problems, you often have what we will call here forces of constraint. So for example, if I've got a mass on a surface, there's a normal force. If I've got a pendulum on a string, I've got a tension in the string. These are what we call forces of constraint, and they can be kind of painful to deal with. You'll remember that the hardest problems you do in mechanics in first year are the ones where you have to deal with all these normal forces and tension forces and break them into components and try and solve. And one of the really nice things about Lagrangian mechanics is often Lagrangian mechanics makes those forces just disappear entirely. You don't have to deal with them, which makes the approach quite a bit easier. Okay, we'll get to constraints a little bit further down in the lecture. So just a quick recap of where we're at, because it's nice to kind of bring everything together at this point. We have generic expressions now for kinetic energy and potential energy. And you'll notice in here, generically, kinetic energy usually depends only on velocities, which makes sense. It's a thing tied to velocity. And then often we have potential energies, and for conservative systems, it usually just depends on position. So we've got positional variables here, okay? And then, as we saw earlier, we can define this thing called the Lagrangian, which ultimately is a function of x, y, z, x dot, y dot, z dot. So it's a function of positions and velocities. That is the kinetic energy minus the potential energy. And as we saw in lecture 3, we decide this because it works, okay? And then this might not be so obvious, but so far we've been taking two types of derivative. We've been taking dl on dx, right? And if you consider what that is, usually the only terms that carry a position dependence are in u, so it really is minus du on dx, and you can see that as basically forces. So dl on dx is just the force in the x direction. The other aspect is dl on dx dot, and this one we did make more of back in lecture 3. It ends up being essentially all of your velocity terms are carried by your kinetic energy. So it's usually something like dt on dx dot, which ends up, if you take the derivative through there, as mx dot, which is basically just p of x, okay? And so you'll remember we called this a generalized momentum back before, and we very quickly pointed out generalized force. If you think about Newton's second law, we know that basically force is time derivative of momentum, okay? And so if you now substitute the corresponding Lagrangian terms down into here, you get dl on dx is equal to d on dt, dl on dx dot. And then if you drag one term over to the other side, you basically get back your Lagrange Euler-Lagrange equation. Okay, so back a few lectures ago, what we did was basically say that Lagrangian mechanics works because we can take the Euler-Lagrange equation and get Newton's second law out of it. What I've just done on this one slide really quickly is go from Newton's second law back to Euler-Lagrange equation. Okay, so just taking the reverse route just to demonstrate that it's fully self-consistent, but you can see taking this path through the maths, it's pretty obvious that this thing does connect and should work. Okay. All right, so that's where we're at now. And then we had something in lecture 3 where we said that we were going to minimize the action, and now we'll give that a name. Okay, so this is a thing that we call Hamilton's principle. Basically says that the actual path that a body follows between point 1 and point 2 is such that the action integral is stationary when taken along the actual path. Okay, I'm not going to do the proof for this specific case right now because it's more or less the same as the proof we did last time to minimize the path, except we're putting the function L inside, and we kind of did that in lecture 3 with a discretized approach. Okay, I'll let you play with that one yourself. It's fairly straightforward to do from everything we know so far. What I'm going to do is do this at the end with a slight twist on it, which is I'm going to prove that it works in the case where we have forces of constraint. Okay, because that's where you get a little slight change in the way you have to set the problem up, and it's kind of an interesting way to see the problem done. Okay, but basically what we have is we've got an action A, which is the integral between the beginning and end points of the path of Lagrangian, and what we do is we set out to minimize the action along that path, or in this particular case make it stationary, right? And the reason why stationary is important is because generally it's a minimum, but sometimes it's actually an inflection or a maximum that's the correct path in here. Okay, because it's usually a minimum, people refer to it as the principle of least action, but you should keep in mind that sometimes it's not the minimum. Rarely, but sometimes. Okay, and so ultimately our Lagrange equation is just the calculus of variations applied to the action on a path in a simple way. Okay, one big observation here, and it's the main reason why I didn't use Hamilton's principle when I talked about it in lecture 3, is I want people to not get confused. At this point, a lot of people start to think, oh, there's a Hamilton's principle here. This must be connected to the Hamiltonian approach in mechanics, or it must be connected to the Hamiltonian in quantum mechanics. It's absolutely not. It just happens to be that Hamilton turns up a little too often in physics, and it makes for some confusion sometimes. Okay, so you'll come across what we call the Hamiltonian a couple of lectures from now. It will just pop out of the maths and we'll have this thing, but it's not connected to this particular place. Okay, it's just that Hamilton had another contribution here that got this principle named after him. Okay, so we have these ideas together. So very quick recap on generalized coordinates, just to make sure everyone's on the same page. We can define a generalized momentum, which we call Pi, which is dl on dqi, and this is independent of the coordinate system. So if it was x, it would be what we saw a couple of slides ago, dl on dx. If it was p of phi, for example, it would be dl on d phi dot. And then we have a generalized force in here, and it's dl on dqi. All right. So I mentioned a couple of lectures ago that I would tell you a really nice mnemonic for remembering which one is which, and I basically remember which one is which as this. If I add a dot to make an F into a P, okay, so let's think about this for a second. If I've got an F and I draw it kind of badly like this, you can imagine I can put a little dot in here and I'll get now get a P. The P is the one with the dot, of course, right? And so the way I remember this is the F in here has no dot. I add an odd dot to the F and I'll get a P, and that's the one I have to add the dot to, okay? And then it becomes really obvious which way around it goes. And then of course you can see that down in here. So this is the momentum part with the dot, and then this is the force term without the dot, and it becomes really easy to remember. I never have to work this thing out, because I basically write just dl on dqi, d on dt, dl on qi, and then I just work out where to put the dot based on where the momentum is, and I know it must be here just from the second law. Okay. All right. So that's pretty much a recap of where we're at. in this half of the lecture, I want to do two things. First is I want to show you that this works for other coordinate systems in the same way that it worked for the Cartesian coordinates that we did earlier. So what we'll do is we'll do Newton's equations for a free body, but this time in polar coordinates, and basically just show that it pops out Newton's second law for that system consistently. And then the other thing I want to address is constraints. So we'll use a pendulum to look at that. And then when we get to the second half, I'm going to deal with some aspects of constrained systems in a little bit more detail, and in particular do a derivation that shows that basically everything holds together for Lagrangian mechanics when you have forces of constraint. Okay, so that'll be the two halves for today. Okay, so let's work our way through here. We've got now we're going to deal with a polar coordinate system. So we still have our y and x, just to give us some context here. We have some body at some position here, and we could write that as an x and y, and we could give it a vx and a vy if we want. Or we could just change our coordinate systems to r and phi here, and then we would have a v that's got components of r and phi. So r and phi instead of v and vx and vy, okay? So let's work our way through here. Polar coordinate problem. So we have a particle, and it's at position r and phi in this particular case, okay? And it will have some velocity that is going to be made up of two components, a vr component and a v phi component. All right. And we know that we can write our radial component just as r dot r hat, where r hat's just the unit vector in the radial direction. Okay, so it would be whatever the change in radius is with respect to time, r dot, pointing in some direction that's radial, plus a polar coordinate, right? And we know that that is essentially a rotational velocity. So it's going to be the radius times the angular frequency, and the angular frequency would be d phi on d dot dt. So this would be r phi dot phi hat, okay? All right, so that allows us to then get our kinetic energy. So our kinetic energy is a half mv squared as usual. And of course, it's going to be a half m r dot r hat plus r phi dot phi hat. And of course, there's a square in here. And so what we need to do is take the dot products through here. Okay, so this would be a half m. To do this in full detail, r dot r hat plus there'll be two terms in here, r dot r phi dot r hat dot phi hat, plus an r squared phi dot squared phi hat, like so, okay? And then we know for unit vectors, r hat dot r hat is equal to phi hat dot phi hat equals 1. So unit vector times itself is always equal to 1. And then the unit vectors are orthogonal to one another, okay? So that will be equal to 0 as a dot product. So at any particular point, r is always going to point perpendicular to phi. If you move to positions, both of those things will follow it round, okay? So this thing ends up being a half m r dot squared plus r squared phi dot squared. All right. And then our potential energy in here, we're going to leave that open. So it's going to be some conservative force system we're dealing with here. And so we're now going to write u as a function of our positions. And of course, in this coordinate system, we're interested in r and phi. So we'll keep this nice and simple like that, okay? Okay, so the next step would be to write our Lagrangians, same as we did in an earlier lecture. And this now, instead of being L as a function of x and y and x dot and y dot, will be L as a function of r and phi and r dot and phi dot, right? So r, phi, r dot, phi dot. And of course, it's going to be t minus u. So in here, we would have a half m r dot squared plus r squared phi dot squared minus u of r and phi, like so. Just slide that over a little. Okay, and so now we've got a Lagrangian that's got two particular terms in it, and so we need to get two Lagrangian equations out, right? There's an R equation, and that's the one we'll deal with first. And there's a Phi equation, and that's the one we'll deal with second, okay? We'll deal with these independently. Why is this not scrolling? Much better. Okay. So this thing would be dl on dr is equal to d on dt, dl on dr dot. And so what we need to do here is, as usual, get the two derivatives that we're dealing with, right? So the first one will be dl on dr, and you can see up in this equation here, there's basically two terms that carry a dependence on r. Okay, so the first one is in the kinetic energy. Okay, so we're going to get a half just here, an r squared just here. So the 2 is going to drop down from the r squared, knock out the half, and so we'll end up with m r phi dot squared. Right, this is just mr omega squared. So you're familiar with what this term is. And then we also have a potential energy term. It's not specified what exactly that term is for the moment, but we know it's got a dependence on r, so when we take the derivative, it's going to survive. So it's going to become minus du on dr for the moment, okay? And then we also care about dl on dr dot, and the only place where that kind of term turns up is in the kinetic energy term. And just here you can see it's mr dot squared. The square from that is going to pop down and knock out the half. So this thing is going to be, mr dot, okay? All right, so now we can take our Lagrange equation in this particular case and build it back up again. So this thing is going to be mr phi dot squared minus du on dr is equal to d on dt of mr dot. And of course, d on dt of mr dot is just mr double dot, right? Because the mass is independent of time. We know this thing in here pretty much straight up, right? It's just the radial version of our force equation. So what this is f of r is equal to minus du on dr. And it's just the radial force component. And if you've done enough mechanics problems in polar coordinates previously, you'll know that the force term for the radial component is the easy one. It's the other two angular components that get a little bit tricky because of the way the calculus works in polar coordinate systems. Okay, so this thing here now we can rewrite as basically f of r is equal to m r double dot minus m r phi dot squared. We can carry the mass out the front. Like so. And then we know what these two components are, right? This thing here is just, let me make sure I put my arrow in the right place. This thing here is just the radial acceleration, which basically means, if my particle's not executing a perfect circle, but it's accelerating along the radial directions in either way, then that's that part of the term, right? And then this part in here is just a centripetal force term, And that requires phi dot to not be 0, okay? And if phi dot is 0, it basically means there's no motion in any circular range, okay? So what this basically tells you is that there has to be a component tied to phi dot, such that if you're doing circular motion, there needs to be an additional force along the radial direction in order to make that particle make a circular motion, okay? So you've basically just got a sensible radial Newton's equation out of dealing with polar coordinates here that now allows for the fact that you might undertake some circular motion in that coordinate system. It fills in quite naturally. We'll come back to this a little bit in one of the later lectures around about, I think it's lecture 13, where we look at how these two coordinate systems fit together in terms of centripetal forces and stuff like that. So we'll come back to the meaning of this term a little bit later on. Okay, so that's one half. The other half in here is we need to deal with the Phi equation. And the Phi equation is similar. You've got dl on d phi equals d on dt, dl on d phi dot. Let's call this one 2 for the moment. And as I was saying earlier, the nice thing about this approach is that the Lagrange equations look the same in every single coordinate, right? So you've seen now the fourth one, because we've done x and y, and we'll do z, we've done r, we've now done phi. They all look the same. We need to get the derivatives, same approach. So dl on d phi here will be, we need to look back up a little bit here to this equation here. Let me just specify what's going on in here quickly. There's only terms in phi in this u here, so the potential energy will be the only thing that comes out here. And then the only terms in phi dot turn up in the kinetic energy, okay? So this one's actually kind of clean just in terms of how you pull out the derivatives. So this one here will be minus du on d phi. It's the only term that has a phi dependence in the whole Lagrangian. And then dl on d phi dot will come from the kinetic energy term. It'll drop down the same way. The square on the phi dot will kill the half. We keep our r squared, and we end up with phi dot, okay? All right, so now we can package this back up into 2. And so what we've got here is minus du on d phi is equal to d on dt of m r squared phi dot, okay? All right, to go any further, we need to deal with the du on d phi. And this is the tricky bit in this part, because here's where the calculus gets a little trickier. You need to pull something you know from your real analysis lectures. So you have basically that force is minus grad u. We dealt with this in an earlier lecture. It's basically the 3D derivative of a 3D potential. And if we do this in spherical or polar coordinates, what we know from our maths lectures is we get du on dr r hat plus 1 on r du on d phi hat. Okay, if you don't remember that expression, go back and look up your maths calculus lectures. You must have derived this somewhere in there. I remember doing it several times in undergrad. But the important thing in here is you can write this thing basically as something that looks a little bit like a, if you put a minus sign here, there'll be a minus here and a minus here, and this would be f of r hat plus f of phi hat. And so you can basically connect these things together, right? So this f of phi here will be equal to minus 1 on r du on d phi. And of course, the thing you want to isolate here in order to deal with the start of this equation 2 will be the du on d phi, right? So we know that minus du on d phi is going to be equal to f phi r. Okay, so we can come back to our equation 2 now, and we can write it as f phi r is equal to d on dt mr squared phi dot squared, okay? And it might be tempting at this point to actually deal with the time derivative on the right-hand side, but you've got to resist that temptation for the moment, because you know that the angular momentum is equal to mr squared omega, right? You learned this in first year. The other way of writing this is mr squared phi dot. So this thing on the right-hand side here is basically d on dt of L, where here L is not the Lagrangian, it's the angular momentum, okay? A lot of you will be going, oh man, this is terrible. We're reusing variables, I'm going to get so confused. One of the things you rapidly hit, usually around the second year, is you realize that there's more maths in physics than there are letters available to cover everything, and so eventually it's unavoidable that you're going to have to reuse letters for some problem. There's just no way to get around it, and so then you kind of have to read it by context, okay? If you're doing it for a problem and it looks ambiguous, just specify what you're doing at a particular point. Okay, so the other thing that we know here is that we have a torque, and the torque is R cross F. And of course, in this particular case, it's going to be R hat F phi sine of 90 degrees, because we're talking about this radial direction in here. And so, actually that's not a hat, that's a, and that's not a hat either, it's a vector sign. And it will be R, that'll be a vector sign just there too. This will be R F phi as a magnitude, okay? If we look at magnitude of tau in here. So this thing on the left-hand side here is basically a proxy for tau, okay? And so what we've got here is basically just now our rotational equivalent. Of Newton's second law, okay? So you can see here we've basically got the same thing out we got in lecture 3 when we did it for Cartesian coordinates. In Cartesian coordinates, it popped out really simply that whether you do x or y or z, they're all the same, that you get F equals ma, which is just Newton's second law, right? Or F equals dp on dt is the better way to see it. Here, when you do it for r, you get the radial force equation, Newton's second law, so you get an acceleration along the radial direction plus a force required to make it go in a circle if it's going in a circle. In other words, if phi dot's not 0. And then you also get down here in this version, if you're accelerating in the rotational direction, then you're changing the angular momentum, right? And that must be via a torque, and so you get Newton's second law, which is basically torque, which is the equivalent of force rotationally, is equal to d on dt of L, which is angular momentum or rotational equivalent of momentum. Okay, so we get our second law back out. It's quite nice, pops out quite cleanly. It doesn't matter which coordinate system you still get the same physics. Okay. All right. So with that done, all that happens in Lagrangian mechanics is if we have multiple objects, we have multiple equations. So you'll know for the problem we just did, we had two coordinates, we had two equations for those two coordinates. If we now had two bodies in that system, both in a rotational coordinate system, we would have particle 1 with r and phi, we would have particle 2 with r and phi, and so we would have 4 equations in here, okay? If we think back to a full 3D x, y, z problem, imagine we have n bodies. Then each of those will have 3 coordinates x, y, and z. Then ultimately in the end, what we will have is 3n Lagrange equations to solve, and every single one of them will look the same. It will look like dl on dqi equals d on dt of dl on dqi dot. And that I will run through 1, 2, 3 for the first body, 4, 5, 6 for the second, 7, 8, 9 for the third, and so on, all the way up to n, okay? And so you can imagine if you're getting very big systems, you've got a very large number of equations to solve and you've got a lot of work on your hands. But in principle, you can do it, okay? Now, that might seem like an intimidating problem, and it is. But the nice thing about Lagrangian mechanics is that often you can deal with a system where you would in principle have 3n coordinates or 3n equations with n bodies of 3 coordinates to solve, but you can use constraints in the system to reduce the number of equations you get so the problem becomes solvable, okay? And so that brings us pretty much directly to constraints. What's Hannibal Lecter got to do with this? Yeah, I said constraints, not restraints. Come on. Okay, sorry, first assistant fail. So we're going to deal with constraints, not restraints. And so far, all the problems we've done in Lagrangian mechanics, and we haven't done many of them, are mostly unconstrained, okay? So particularly the problem we just did then, free body can go anywhere it wants. There's one body, there's 2 possible coordinates for it, since we've restricted it to a 2D system. And we have to solve all of the equations for all of the coordinates in there, okay? A major benefit of Lagrangian mechanics is that it also works for constrained systems, like being on a wire or a rigid body made of atoms where the spacing between the atoms is rigidly fixed, so it's a constraint, right? This atom must be a certain distance from the other one, the whole body moves, and everything moves similarly because of this constraint between the separations, okay? And in a lot of cases, constraints are nice in Lagrangian mechanics because they make the problem simpler, whereas in Newtonian mechanics, they tend to make the problem harder, right? If you think about constraint forces in Newtonian mechanics, you've got things like the normal force to stop things from falling through tables. You've got like the tension in a wire or the tension in a string or whatever it is. You have to deal with that as an extra force on top of all the other forces in the system. So constraints actually add complexity to problems in Newtonian mechanics rather than remove them. In Lagrangian mechanics, constraints actually remove complexity from the system because they reduce the number of Lagrange equations that you have to solve in order to get to the end of the problem. You go from 3n to as few as a few to solve in here, okay? And so to give you some insight for how this works, I'm going to do this with the pendulum problem, okay? Oops, wrong color. Right, constrained systems. So we have our familiar old pendulum. It's a hinge point up here at the top, we'll call it O. We drop down here to where the body would be when it's not swinging, and of course it will swing out in some direction here. So you can make this solid because it's out there. Length L on the string. Let's call it a rod, so it's a solid rod, right? So we can really imagine that this thing can't move anywhere aside from being constrained to the end of this rod. We got some mass M. It would swing backwards and forwards, and of course we can work out what height it has above that equilibrium position here. We can define our coordinate y pointing downwards here like we have in the past. And know that this length here is L minus h, and this swing angle here is phi. Okay, so we've nice and cleanly specified this system. Okay, so the system is constrained in 2 ways. You can imagine here what we've got is a body that in principle could go anywhere in 3D space, right? And it doesn't. It's basically just swinging on the end of this rod. So we've got 2 constraints. One is it's not going to go out of the plane of motion of the pendulum, right? So no motion in Z. And then we also know that if we consider x to be this direction, y to be this direction, there's a constraint on the x and y such that it's always x and y in such a way that it's got a fixed distance from the rotation point up here, okay? So my particle's here, it's got distance L to here. If it's here, it's got a distance L to here. If it's here, it's got a distance L to here, okay? And so basically what we can say is that L, which is equal to square root of x squared plus y squared, is a constant. And what that means is, from the first constraint, we don't care about z at all. And from the second constraint, actually, what we can do is, if we wanted to, we could just write y as a function of x, right? So y is equal to square root of L squared minus x squared. And we know for every position of x, we know the y, and so we could deal with just the one coordinate y or just the one coordinate x in this problem and keep it nice and simple, okay? So the two constraints here have basically eliminated two of the three coordinates that we would have in our problem. And by association there, they've also eliminated two of the three Lagrange equations that we have to solve. Okay, so what happens here is the constraints made the problem easy because instead of having to solve three Lagrange equations, we only have to solve one. And we can be even smarter here. What we can do is swap coordinates. We can go from x and y to like a radial coordinate, so like a r and a phi. And we can basically just say that r is fixed at L and phi is the only coordinate that can change, okay? And so we're going to do an implicit coordinate change here. We're going to parameterize in a single coordinate phi, okay? You'll notice I mentioned a couple of times earlier on when I've done Lagrangian problems as examples that you have to think about constraints, and I talk about it later. This is exactly the thinking that you go through, right? You look at the way the system's constrained and you try to work out how to reduce your set of variables down so that you can then reduce your number of Lagrange equations down, okay? All right. So this ends up being pretty easy in here now. We can basically just consider the mass on the end to be doing a radial motion, okay? So our kinetic energy is kind of easy. It's a half mv squared. It's constrained so its radius can't change. So the only term that's in here will be the phi dot term. And so it's going to be a half m L squared phi dot squared in here, okay? So L phi is basically r omega, and so we're really just putting a circular motion term in here. The potential energy is mgh, and of course we've got to work out what our little h here is in terms of our new coordinate phi, okay? Now one thing we know is we can use trig to get the phi, and we know that cos phi up here, if we're dealing with cos, it's adjacent over hypotenuse, so it's going to be L minus h on L. We can isolate h, so this is going to be L minus h is equal to L cos phi. H equals L minus L cos phi, and we can pull the L out, so this is L1 minus cos phi. Like so, okay? And so now we take the next step, we write our Lagrangian, right? Is t minus u, and so it will be a half m L squared phi dot squared minus mg L1 minus cos phi. Pretty straightforward, okay? And now we've only got one equation to solve because we've used our constraints to knock the other ones out. We haven't proven yet definitively that Lagrange's equation works for constrained systems. I'm going to do that in the second half. So for the moment, we're going to use a result that I'm going to prove later, but I'm going to prove it later, so everything's going to be hunky-dory, right? So we have one Lagrange's equation to deal with here, which is really just dl on d phi equals d on dt dl on d phi dot, and this is momentum, so the p is on that side. Sorry, the dot is on that side. Okay, so we need to work out what the two derivatives are first. dl on d phi. We can see it up here. The only term that carries it is this cos in the potential energy. So that thing is going to be minus mgl sine phi. And of course, the front end of that term drops out because it's got no terms in phi. And then we need to get dl on d phi dot. And it's easy. It's up in this kinetic energy term. Same again, the square drops down and knocks out half. So this thing ends up equaling ml squared phi dot in this particular case. Okay. So now we can pull this all together and write our Lagrange equation. So minus mgl sine phi is equal to d on dt of ml squared phi dot. And then, of course, in this particular case, m's a constant, l's a constant, phi is the only thing time dependent. So this will be ml squared phi double dot. Okay. And if we think about this thing for a second, we're going to get what will seem like a trivial result. And that trivial result was not the point of the problem. The point of the problem is what we'll follow in a second. Okay. So if you think about this term on the left-hand side here, what it is a force acting about a center. Okay. So if I'll let you work out the full details of the cross product yourself, this thing is just the torque. Okay. And then if you remember back to your first year lectures, if you've got a body of mass m at some distance r from a point of rotation, the moment of inertia for that body I is just mr squared, right? So this bit here is just I, and then phi dot is omega, phi double dot is alpha, the angular acceleration. So this is just the angular acceleration in here, okay? And so this is just a rotational equivalent of Newton's second law, okay? So Newton's second law would be F equals ma. This is torque equals moment of inertia times angular acceleration, okay? Anyway, if we wanted to understand the motion more, we could take this differential equation up here, we could solve it, and you can do that for yourself if you want to play around with it, and you can work out how phi behaves as a function of time for this problem. Okay, I don't want to go there because it doesn't really get us anything new in terms of this lecture. The really crucial thing I want to finish up here before I take the break is you'll notice that we did something kind of cunning in here. We went from a set of Cartesian coordinates that, let's for the moment call them r of alpha, that are x and y and z, and we can go to a set of generalized coordinates from there, qi, which in this case are like, you could imagine an r and a phi, but we even killed r by making it l, so it could just be a phi, okay? And we can go interchangeably between these two things. And we did that in this particular problem. We went from x, y, and z to polar coordinates and back. And you can switch between these and make the problem equivalent. And you can deal with constraints in this way as well. Now, the interesting thing you'll notice here is that there's n coordinates here, where n is equal to 3. And in my generalized coordinates, once I've done the Lagrangian version of the problem, I've got an n, which I'm not going to call big N, because now it's not equal to that. It's equal to 1, right? And you'll notice that for an unconstrained system, if we think about, you know, taking away the rod and just letting the particle move around, we would have to have r and phi and a theta in here to describe those three coordinates. So now our n would be 3. And so in an unconstrained system, big N equals little n, or the number of generalized coordinates is equal to the number of coordinates that you have for the whole system, right? And if we had 2 bodies, it'd be 6. It'd be 3 bodies, it'd be 9, and so forth. The nice thing about constraints is that the number of generalized coordinates, little n, can be much smaller than the number of coordinates, big N. And constraints enable you to reduce the number of Lagrange equations that you've got to solve. And you can do it in such a way that you don't have to see the force of constraint in here. You'll notice in dealing with the problem up here, if you did this problem with the pendulum in a Newtonian perspective, you would have a tension force in here that you'd be balancing off against mg, and you'd have to break up into components tx and ty and do all this stuff, right? You've got a force of constraint you've got to work with to solve the problem. You notice all the way through this Lagrangian approach, the tension in the string never turns up, and yet we can solve the problem almost all the way to the end, actually. And you can go all the way to the end. You can get phi as a function of t and never deal with as time t, and never deal with the tension big T in the problem, okay? And this is one of the really nice aspects. And for our pendulum, we kind of just went from, you know, n equals 3 to n equals 1. We reduced the number of coordinates down. But if you imagine, for example, trying to work out the dynamics of a blob of metal, for example, like 1 mole, your n would be like 10 to the 24, right? Because you've got a mole of individual atoms, all of them have 3 coordinates. But when you apply constraints to this system, such that, you know, each one has to sit a certain distance from its neighbor and it has to maintain that distance, you can reduce the number of coordinates for that system down to 3 or 6 or something sensible like that, right? It might be 3 translation and then 3 for rotational directions. And so one of the nice, powerful things about Lagrangian mechanics is you can take very difficult mechanical problems and reduce them down using forces of constraint, okay? So we'll take a bit of a break here, and when I come back, I'm going to deal with the one overhanging issue, which is properly defining Lagrange's mechanics working under forces of constraint. So let's take a break here.